Recording, we are live in 3, 2, we're already live. Okay, cool. So we're talking all about roller coasters today. More specifically, it's the loop-de-loop, okay? The top of the loop and the bottom of the loop. And we're back. So roller coasters, top of the loop and bottom of the loop, that's really all we care about. We don't care about the sides, we just care about top and bottom. So let's talk a little bit about roller coasters. All right, so let's see, roller coaster math here, okay? Okay. Remember I told you, there's only 2 points in a loop, specifically with regard to roller coasters, that we care about. The first part is when the car is at the top, and the second part is when the car is at the bottom, okay? So here we have the top of the loop and the bottom of the loop. All right? Okay. So there are forces that are acting on these cars. If there were no forces, you would just fall right out when you're at the top. But you don't. You are pushed against the top. You feel that centripetal motion with a P. You're getting pushed out, so you think you're feeling the centrifugal motion, and we don't like centrifugal. Because it's a loop, there is a center part, a center point on each, which allows us to determine a radius for each. So notice, this is circular motion. Again, we have a radius, the top of the loop and the bottom of the loop. Okay. Now, looking at this, there are specific forces that are acting on these cars. Okay. The first force that acts on both of these cars is the force that acts on everything, and that is gravity. Gravity, if you remember, always points in the downward direction. So it doesn't matter where the car is, top, bottom, side, here in Mars, gravity is always pointing towards the center or down. So gravity, F of G points down, in this case, towards the center of the circle. When we go over to here, gravity will still point down, but it's not pointing towards the center of the circle anymore. F of G. All right. Now, there is another force that presents itself as well. And that other force is the force that is present whenever an object is in contact with a surface. And hopefully you remember, when an object is in contact with a surface, it is the normal force that presents itself. Remember, the normal force is always perpendicular to the surface. For example, if this is my surface, this piece of paper, and I put a pen on it, the normal force will be pointing up. If this is my surface now, and I hold a pen against it, the normal force is pointing out. The normal force is always pointing perpendicular to that surface. So notice, if the surface is up here, the normal force will be pointing down. It's pushing against the object. Fn, normal force in gravity. Over here, this is something that we're more familiar with. It's like us sitting down on a bench or on a seat, a pen on a desk. The normal force will be pointing up. So there is a major difference right there. In this case, when the roller coaster is at the top of the loop, both the normal force and the force of gravity push in the same direction, and that is down. In this case, when the roller coaster is at the bottom of the loop, gravity pushes down, but the normal force is pushing up, opposite directions. All right. Now, there's one more force that I want to bring your attention to, and that is the centripetal force, F of C. Now, remember, when we first learned about F of C, we said that its identity could be any force or combination of forces that make an object go in the circle. Well, guess what? When an object is at the top of the loop, both the F of G and the F of N are making that object go in a circle. So these two together make up the centripetal force. So F of C equals both the F of N plus the F of G. And I am adding them both together because they're going in the same direction. I know they're both going down, and down is usually indicated by a negative, but if they were both negative, there's no difference. Both negative, both positive, it's the same result. Now look over here. Major difference. Here, the F of C is still a combination of F of G and F of N, but they're in opposite directions now. The F of N is positive, but the F of G is negative, and that's where that negative comes from, that subtraction. Okay. So those are the two main roller coaster problems or formulas. So what we'll do is we'll throw those right over here. Let's see, I'll throw them right down here. So for the top of a loop, F of C equals F of N plus F of G, because they're going in the same direction. And for the bottom of a loop, F of C equals F of N minus F of G. Now we could actually break these down one step further. We could say that F of C equals F of N plus F of G is really just mass times gravity. And over here we could say F of C equals F of N minus M times G. And we could use those, you know, if our variables are slightly different or something along those lines. All right, so that is really it for the notes. So what I would like to do is I want to go over the first example in your homework. So if you could all go to the assignments page, and open up the roller coaster problems. You'll see it's a 4-problem sheet. And we'll do the first one together. It is the roller coaster practice, and we'll do the first one together. All right, just let me know when you guys are all set. Don't worry, I'll cut a lot of stuff out. It'll be seamless. All right, everybody good? Everybody got that first question up? All right, so if we're looking at the first question, question number 1 for practice. Analytical is riding the Shockwave at Great America, the roller coaster. Anna experiences a downward acceleration of 12.5 meters per second squared at the top of the loop and an upward acceleration of 24.0 meters per second squared at the bottom of the loop. Use Newton's law to determine the normal force acting upon Anna's 50-kilogram body at the top and bottom of the loop. So what I'm going to do is I'm going to leave these drawings up here and I'm going to add in that information. At the top of the loop, she experiences a downward acceleration of A equaling 12.5 meters per second squared. At the bottom of the loop, she experiences a downward acceleration of 24.0 meters per second squared. And we want to determine the normal force for each. We want to determine the normal force for each one. Okay. And we know that the mass of her body is 50 kilograms. M is 50 kg. M is 50 kg. Okay. So how can we plug this in? What I'm going to do is I'm going to erase this equation right here. That way we can just deal with that one. How can we use these equations to find the normal force? In both cases, we're looking for the normal force. All right. We have an M. We have a G that's 9.8 meters per second squared. So we know those. We're looking for the Fn, but how can we find the F of C? Well, if we think back and look at our centripetal force equations, we see that Fc equals mv squared over r. Fc can also equal, and I know you've done this in some of your other problems, m times ac. Because remember, if we have the centripetal acceleration, which is v squared over r, that's the same thing. So it's really just mass times centripetal acceleration. That's what the F of C is. So it's really just the mass times the centripetal acceleration equals the normal force plus the mass times gravity. And then all we have to do is plug it in. 50 times 12.5 equals the normal force plus 50 times 9.8. From there, grab my calculator. From there, 50 times 12.5 is 625 F of n plus and then all we have to do is subtract. And we find, I'm going to write it up here, we find that the normal force comes out to be 135 newtons. 135 newtons. All right. Now we're going to do the same thing for the other side. But we have some different variables. So over here, we're going to do the same thing. M times AC equals Fn minus mg. Her mass is still 50. Her new acceleration, notice the accelerations do change. When you're at the bottom of the loop, we were told that the acceleration is 12.5. When we're at the, we're at the top of the loop, the acceleration was 12.5. When we're at the bottom of the loop, the acceleration is 24.0. Hey everybody, so I did make a mistake here. You'll notice that multiplying 50 times 240, we have 1200 newtons equals Fn minus 490. What I did in the video was I subtracted the 490 from the 1200. On one side, that is incorrect. What I'm writing now is incorrect. What I should actually have done was did the opposite of the subtracting of 490. I should have added 490 to both sides. So adding 490 to both sides would give us a normal force of 1690. So 1690 should be the answer. And I'm going to go ahead and put that in right now. You'll see the normal force should be 1690. So I'm just going to continue with this voiceover for the rest of the video. You'll see that the normal force when the car is at the top of the loop is far less at 135 newtons than when it's at the bottom of the loop at 1690 newtons. You feel more of a force pushing on you by the seat when you're at the bottom of the loop. You feel more G's pushing down on you. That seat is pushing up on you with a greater normal force. When you're at the top of the loop, you almost feel like you're falling out. And when you're falling out, there's less of a normal force pushing on you. Okay, so your normal force should always be lesser at the top and greater at the bottom. All right, guys, I hope this helps you to understand roller coaster problems, top and bottom. Make sure you watch that normal force and watch that force of gravity. All right, best of luck, everybody. Bye-bye.